Okay, we're going to talk about moment generating functions. And we've used this term a couple times already this semester, but here's just a reminder about the definition. The nth moment, and then a little bit more precise, the nth moment about the origin of a random variable x is defined as the expected value of x to the nth power, and this is for natural numbers x, right? So we talk about the first moment, the second moment, the third moment, and so on. A couple of precisions, a couple of notes about this. X can be discrete or continuous. It does not matter. There is another kind of moment, and if x has mean mu, then the expected value of x minus mu to the n is called the nth central moment. So obviously if mu is 0, then these guys are the same thing. But if mu is non-zero, the nth central moment and the nth moment about the origin are not the same. So another name for the nth central moment is the nth moment about the mean. So as we know, mu, which is e of x, is the first moment about the origin, right? That's x to the 1, so n is equal to 1. The variance, sigma squared, well, actually, the definition, we're not used to using this. We use the computational formula typically, but the definition of the variance is the expected value of x minus mu squared. Compare that. Compare that to the central moment. So the variance is actually the second central moment. But if we use the moments about the origin, there is a formula that uses that too. So the variance is related to the second moment about the origin, but it is actually the second central moment. And so going forward, we're actually going to be focusing on moments about the origin, and so I'm going to stop saying about the origin. When I say the nth moment, I'm going to mean this. I'm going to mean about the origin, not about the mean. And so the nth moment, I'm going to mean the expected value of x to the n. So using that, if x is a random variable, discrete or continuous, the moment generating function is called m of t typically. So t is this, well, what is t? T is just a dummy variable. It is a variable of convenience that is going to let us create this function and going to let us calculate moments. So t is just a variable of convenience. So m of t, the moment generating function for x, is the expected value of e to the tx. So that's a little bit of a strange definition. It's going to be very useful, and we'll see why in a little bit. But that is the moment generating function, right? This t is going to hang out through this calculation of the expected value, and this expected value, that is the expected value of a function of a random variable, e to the tx. E to the tx is a function. It's a function of x, and so Lotus is going to tell us how to calculate that expected value, and since t is just a symbol that is going to hang out there, the end result will still have a t in it most typically. Now there's one little caveat. And that is provided that this function is finite on some interval containing 0, and quite particularly at 0 as well. Okay, so that is the moment generating function. So it seems strange, it seems weird for a definition. So let's go and explore that a little bit. The first thing is, why? Why do we want this? Why do we want a moment generating function? Well, you might guess that it generates moments. That's what it does. So it calculates moments. It lets us calculate moments easily. Not that the first moment, the mean is terribly difficult to calculate in most situations, but this function makes all the moments much easier to calculate. But perhaps the more important reason that we want this is there are going to be some properties of the moment generating function that we're going to look at a little bit later that are going to help us identify distributions. So when you've got a transformation and you don't know what it gives, the moment generating function can be exceeding useful. And also moment generating functions are going to be useful about or for proving some results about sums of independent variables, some that you have used in your previous course without proving. And the moment generating functions prove that those results about sums of variables are in fact true. So that is the why. We're going to go in the rest of this lesson and concentrate on this part about calculating, first of all, calculating the MGF itself, and then using it to calculate moments. And this second part will come to a little bit later. So let's go ahead with calculating moments. And we have this little theorem. So if m of t is the moment generating function, so defined as we had above, the moment generating function is the expected value of e to the t times x. That is the moment generating function for x, and very often when we've got more than one variable around, we put a little subscript, just like we did for the marginals distributions, m sub x of t. But if there's only one, just like with the density, if there's only one variable around, you don't have to specify. And so m of t is a fine notation when we only have one, when there's only one variable. So if m of t is a moment generating function for some random variable x, then two things are true. One, m of 0 is equal to 1. That is always true for a moment generating function. And also that the nth derivative, that is what that superscript means. So written another way, the nth derivative dn by dt to the n of m of t is the nth derivative. The nth derivative evaluated at 0 again. So now we're understanding why we need this function to exist and be finite in a neighborhood of 0. So the nth derivative evaluated at 0 is the nth moment. It is the expected value of x to the n, the nth moment. Hence, moment generating functions. And one could even go a little bit further, right? This is for n as the natural numbers. If you think about this, while using a property of the expected value, that's the expected value of 1, and that's the expected value of x to the 0. And so you could actually express, you could say this is a property of like the 0th moment, which we don't usually speak about, but it is kind of consistent. It is kind of consistent with the rest of the formulas. So let us go ahead and look at the proof of this theorem. So part A is very simple. If we've got m of t is e, the expected value of e to the tx, then m of 0, plugging in t equals 0, right? This is putting in t equals 0. Then I'm putting in t equals 0 in the expected value as well. 0 times x gives me the expected value of 0, e to the 0, which is e to the 1, which is 1. So there it comes out actually really, really quickly. So part A is very simple, but it is a property of all valid MGFs, a property of all valid MGFs. The second, so actually I just caught myself saying something there, MGF, moment generating function. So I very commonly, and not just me, it is very common to refer to moment generating functions as MGFs because that's what the cool kids do. So next, part B, proving the nth derivative property, that the nth derivative evaluated at 0 gives the nth moment. We are going to use Maclaurin series. We're going to use Maclaurin series information from your Calculus 2. And your Maclaurin series, you remember, is a Taylor series about 0. And the definition is that f of x is equal to, if the Taylor series converges, if the Maclaurin series converges, then the function is equal to this formula, the sum from n equals 0 to infinity of the nth derivative of the function evaluated at 0. This is the Maclaurin series, so evaluating at 0, of x to the n over n factorial. And that is the definition of the Maclaurin series. And if the function converges, if the series converges to its function, then the function is equal to that. We also have an application of that. If we take f of x equal to e to the x, and this is a result that you might remember from your Calculus 2. If not, it is very easy to see. The nth derivative of e to the x is just e to the x. Whoops, not e to the 0. That's coming up. It's e to the x. All right, if you take the derivative of e to the x, you get e to the x. So if you evaluate that at 0, you're going to evaluate it at 0, and you get e to the 0, which is 1. So that here, the nth derivative evaluated at 0 is like a 1 times, and then the rest is still there, x to the n over n factorial. So e to the x can be written as this Maclaurin series, and that is actually valid for any x that converges on the entire real line. So using those two pieces of information, we're going to go ahead and prove B here. So m of t, the moment generating function for x, is defined, this is the definition, the expected value of e to the tx, replacing e to the tx, right, by the Maclaurin series. If I take the x here, and replace it by t times x, so the x here gets replaced by t times x. So we have the expected value of this series. Now, we're going to do a little bit of a switcheroo here. The expected value, we know that the expected value is linear, and so it might not come as any surprise to you that you can switch the sum and the expected value, but there is this little complication of going to infinity. Does that get in the way or not? It shouldn't be immediately obvious that you can do that, but in fact it is justifiable for an absolutely convergent series in this case. And so that step should raise some eyebrows, and it is perfectly permissible to switch the expected value and the sum, to use the linearity of e on an infinite sum. So we get the sum from n equals 0 of the expected value of that same inner part of t x to the n over n factorial. Now these things here, right, t is a constant, n, and therefore n factorial is a constant. You can bring those out, again using the linearity of the expected value. Bring those out and you get this. So you get the expected value of x to the n is what is left, and the t to the n over n factorial has come out. Now wait a moment, hold the phone. This looks awfully similar to the Maclaurin series. It looks awfully similar to the Maclaurin series. In fact, t to the n is absolutely right there. N factorial is absolutely right there. And if I apply this formula to the moment generating function, so instead of f we use m, then the factor, which is right here, is the nth derivative of m evaluated at 0, and that therefore must be the e, the expected value of x to the n, right? So by using this property up here, number 1, the nth derivative of the moment generating function evaluated at 0 gives you the expected value of x to the n, the nth moment about the origin. So there's the proof. There's the proof for this theorem. So we are going to do a couple of examples, one discrete and one continuous. So example, let's let x be a discrete random variable with probability mass function given by this table. We're going to calculate m of t, the moment generating function, the MGF for x. We're going to use that MGF. We're going to use that MGF to calculate the expected value of x squared of x cubed. In other words, the first, second, and third moments, and the variance using the MGF. And then we're going to go back and calculate those values as we would have done before we knew about MGFs using Lotus, using the rules of the expectation. So let's go ahead and do that. So if we look at the solution here, the moment generating function, this is the definition, is the expected value of e to the tx, is the expected value of e to the tx. That is the definition. Using the expectation, this is an application of Lotus, right? This is a function. This is a function of a random variable, and Lotus tells us that we take that function and we place it in front of the PMF, right? So that is an application of the Lotus theorem. So we're summing over all values of x of e to the tx times the PMF. Well, that's pretty easy since we only have a little table here with 3 values of x. So we're taking the x value, e to the tx. This is, whoop-de-daisy. We have, Houston, we have a problem. These are not supposed to be x's, they are supposed to be t's. This is a function of t after all, right? So this is supposed to be e to the t times x. So I have my first value of x is minus 2 times t. My second value is 1, so 1 times t. And my third value is 3 times t. I'm going over the value of x, right? But I also have to multiply by the PMF. So p of minus 2, e to the minus 2t. P of 1, e to the 1t, and P of 3, e to the 3t. There is a calculation for the MGF. So that is m of t. That is m of t standing right here. Right? This function, right, this moment generating function has to exist on an interval that includes 0 for this to be valid. Well, this function here is finite on minus infinity to infinity, so this is indeed a valid MGF. So there is the moment generating function for our random variable x. Now, that was part A. Part B says use the moment generating function. So what have I done? I have, wow. Sometimes I astound myself with my ability to ignore what's on the page. All of these should be t's, so let me go ahead and change those. We are taking a function of t, right? We are taking a function of t and taking derivatives, so all of my variables should be t. So that is now corrected for us. So we want the first derivative. Why do we want the first derivative? Because because the derivatives, right, the derivatives of the moment generating function, the nth derivative of the moment generating function, evaluated at 0 gives me the expected value of x to the n. So if I want n equals 1, at n equals 1, that's the first derivative. At n equals 2, I'm going to need the second derivative. And n equals 3, I'll need the third derivative. So let's calculate those derivatives because we need to calculate the expected value of x equals x to the 1, of x to the 2, and of x to the 3 because the question asks us to. So let's go ahead and calculate those derivatives using the chain rule. Using the chain rule, the derivative of e to the minus 2t is e to the minus 2t times minus 2. So that minus 2 comes and multiplies the 0.3. The same thing here. The derivative of e to the t is just e to the t, so I get the same term back. And then the 3 comes down and multiplies the 0.5 to give 1.5. There is the first derivative. Going on and calculating the second derivative using the chain rule, you are going to get this calculation. And using the third derivative again, you are going to get this result. With those, right, those derivatives, the first, second, and third derivative, if you evaluate at 0, then you get the expected value. So the expected value, right, x to the 1, the expected value is the first derivative. Evaluated at 0, plug in 0, e to the 0 is 1, and so you have to add up all the coefficients and you get 1.1. X squared, so the second derivative evaluated at 0, right, gives you, again, all of these. E to the 0 gives 1, so you're adding up those coefficients and you should get 5.9. X cubed, third derivative evaluated at 0, add up the coefficients, 11.3. And then the variance. The variance is using the computational formula. E of x squared minus e of x all squared. We have those values sitting up here, e of x squared, e of x. Plug those in and you should get 4.69. So the third part, that's B done. The third part asks us now to calculate the same values as we would have done using Lotus. So we will go through this really quickly and see, but using Lotus, the expected value of x, you would have done this calculation, the sum over all x values of x times the probability mass function. If you do that, you will indeed get the same 1.1 that you did above. E of x squared times the probability mass function summed over all x values, you'll get the same. And the last, e of x cubed times the probability mass function, you will indeed get your same 11.3 as above. So for the discrete case, in a small case like this, perhaps not much advantage. You might say, really, this seemed like maybe more work than this. So why would I bother? Well, it's a fair question. Let's look at another example, and then I will remind you that there are some theoretical results that the moment generating function allows us to prove. So one more example for calculating here. Let's look at a continuous case. So let x have density this, e to the minus x, for x greater than 0 and 0 otherwise. We are going to calculate the moment generating function, and we are going to calculate the first 3 moments and the variance again using the moment generating function. And then I'll make a little comment about what if we had to do it by hand using Lotus. Not that this isn't by hand, it's just a different calculation. So using the definition for A, the moment generating function is the expected value of e to the tx. You should be getting used to that now. That is the definition of the moment generating function, as long as that function is finite on some interval containing 0. So for this variable up here, right, we are using Lotus, so we are taking the function of the random variable times the density over the support of x from 0 to infinity. Now, x is our variable of integration, which means that t in this integral is a constant. T is just a constant. So we can go through and do some algebra here, law of exponents, bring those two with a common base together and factor out the x, and we get e to the t minus 1 times x dx, right? A little u substitution, which I use the variable u for my limit, but a little substitution, whether you call it u or v or w or whatever, will tell you that the antiderivative that you need is 1 over t minus 1, e to the t minus 1 x, and then this improper integral from 0 to infinity becomes the limit as u goes to infinity of this antiderivative from 0 to u. Now this here, depending on our values of t, this may or may not converge. And we want a moment generating function to be finite. We want it to converge in a neighborhood of 0. So we have to examine this and see when will this converge. And this will converge here if the power in front of x, the coefficient, I should say, in front of x, is negative. And if that is negative, then we are going to get e to the negative infinity, which you know is a shorthand for something that is going to 0. So in the situation where t minus 1 is less than 0, which is like saying t is less than 1, then this here will tend to 0. And we will get as an answer minus 1 times 1 over t minus 1, or flipping the signs around, 1 over 1 minus t. This is valid, right, where that limit converged, and so that is on t less than 1, and that is an interval that includes neighborhoods of 0. So this is indeed a valid moment generating function. And just again, let's just quickly notice that property. If we plug in 0 at the beginning, before taking any derivatives, then we're verifying this property that m of 0 equals 1. That was part A of the theorem. So the question asks us to calculate moments. So we are going to calculate successive derivatives of the moment generating function. And if you apply the chain rule correctly, you should get these as your three derivatives of the first three derivatives of the moment generating function. The expected values, e of x to the 1, the expected value of x is the first derivative evaluated at 0. That gives you 1. E of x squared is the second derivative evaluated at 0. That gives you 2, right? That coefficient of 2 here. And the expected value of x cubed is the third derivative evaluated at 0. That gives us 6. And of course the variance e of x squared minus e of x all squared, well, if I use those two values and plug them in, 2 minus 1 squared gives me 1. So in the discrete case, we said, well, this doesn't look like it's a whole lot less work. Well, let's compare here. If we were going to do the expected value of x cubed by Lotus, if we were going to do this by the theorem, which tells us we'll just put the function in here, well, you would have to do integration by parts 3 times. And if you wanted e of x to the 4, you'd have to do it again and again and again. Whereas the moment generating function lets you take simple derivatives and you get all of your moments very, very quickly. So it can actually save a bit of time for generating moments. But as I say, the most important properties, probably, of the moment-generating functions are its theoretical properties, which we are going to move towards in future lessons.